Hi, this is the second lecture in reinforcement learning, and today we will discuss Markov decision process. Basically, we will first look at the motivation for the Markov decision process. Then we'll look at the Markov process, Markov reward process, and finally in the progression we reach the Markov decision process. We'll see how they are related. We will discuss examples extensively. And before I get into my lecture, I should acknowledge my references here, and which I recommend. Reinforcement Learning by David Silver, very good reference, and so is the Stanford course on artificial intelligence. Okay, so what is the motivation here for the Markov decision process that we are studying in this lecture? Basically, we stated in an earlier lecture that this is the agent here, and our agent receives from the environment the words and the observations and produces actions. Okay, and what we want is to maximize the future rewards generated by the agent. Okay, so this is to maximize those rewards. We have this agent must be capable of generating maximum reward actions. Okay, so we will look into how we can generate those actions which at the end provide for me maximum rewards, because as we stated in earlier lecture, that the purpose of the agent is to maximize future returns or future rewards. Now, in this lecture, we will do so by constructing Markov decision process, which is right here. Okay, and we will try to solve for optimum policy, which maximizes the value function, the state value function, and the action value function, and in return this should maximize the rewards. So again, to restate or to recap here, is that my objective is to maximize the rewards. We will have to find out those actions that will return the maximum future rewards, and to do so we need to design this Markov decision process, or to be more accurate, solve it. Okay, and in doing so we determine the optimum policy which provides for me the maximum value function, maximum state function, maximum state value function, and maximum action value function that will provide for me maximum rewards through the actions. Okay, so our focus will be on the Markov decision process. However, as we will see here, that the Markov decision process is a progression of different level of processes, and we start in this level of progression by stochastic random process. And in the stochastic random process, if you add to it the Markov property, then it becomes Markov process of Markov chain. If you add to the Markov chain rewards, then it becomes Markov reward process. And if you add to the Markov reward process actions, then it becomes Markov decision process. So really, Markov decision process is what? It is a random or stochastic process with which satisfies Markov property and has rewards and actions. Okay, so this is basically the Markov decision process. Now, what is Markov property? Markov property is, let me just select a different color here. The Markov property basically states that if you know the present state, then you can, this is enough to determine the next state. You don't need to know the history. Okay, so here the probability of determining the probability of determining the next state given the present state is equal to determining is equal to the probability of determining the next state given the history of all state, including the present state. Now, so the idea really, you don't need the history. The only thing you need is the present state. And this significantly simplify the designs, because imagine if you are running a process days in and days out, and you need to make a prediction. Then you have to know the history of this process, which can be millions of previous states. But if the only thing you care about is the present state, then you have simplified the process. And this is basically the Markov property. Okay. An excellent example, if you look at the pseudo counter here, the counter value, the current counter value, it tells you that you are in count, for example, 5, and a pseudo-random counter, we know it is cyclical, so you know really where that count came from. So it is enough to indicate a count of 5, and you don't need to worry about the previous states of the count. The current value is good enough. Okay. Now, with that, we can define a Markov process as a random process, memoryless random process, and satisfies the Markov property. And it has it's basically a tuple where you have the first one is a set of states, and the other is a state transition probability matrix. State transition probability matrix. So this transition probability matrix tells me that if I want to move from or transition from state S to state S prime, then it provides for me that probability, right? Okay, so it provides for me that probability. Now, so for example here, so the transition probability matrix can be represented by this structure, this matrix here, where you have basically the rows are the states, right? This is from this state to this state, from this state to this state. Okay. One thing important, that each row must add up to 1, which makes sense because you are indicating the probabilities of transitioning from a specific state. The sum of those probabilities must add to 1. Now, here is an example which I took, excuse me, which I took from the earlier stated reference by David Silver. Excuse me. And I modified it slightly here. So basically we are taking a course, and in this course we need to go through class 1 and class 2 and class 3 and pass exam, and then we finish the course. We go to sleep state. While I'm going through class 1, there are these distractions. And in class 1 I can be distracted by the phone with a probability of 0.5, or I could go to class 2 with a probability of 0.5. Okay, so while I'm playing with the phone and checking my messages and watching videos and social media stuff, etc., the probability of me staying in that state is 0.9. The probability of exiting that state is 0.1. Okay, and you can go through the example here. And the important thing here is that in this example is that it shows that this series of classes that you need to take to finish a course, and with certain distractions that come in the along the way. Now, for class 2, there's a probability of 0.2 that you go to sleep and never finish the class, unfortunately. And class 3, there is a probability of 0.4 you go to the cafeteria, and then in the cafeteria you want to drink coffee, chat with friends, and and then there is this probability of 0.2 going back to class 1, 0.4 going back to class 2, 0.4 going back to class 3. Okay, so some machine. So here are the possible episodes or sequence of states, C1, C2, C3 past sleep, and this is basically, if I may change, whoops, sorry, if I may change the color here. See, so for this one here, this represent the series of states. All right, and we can have a different sequence, C1, C2 cave, C1, C2 sleep, which is, and this one here I can let's change the color here. So red for this one, this is red, C1 class 1, class 2, and then class 3. Then I go to the cave, the cafeteria, and then back to C2, and back to C2, C3, right, C3, and then pass and go to sleep. So this is another sequence. You can think of many sequences you want, but in this case, my starting my state S1 equals C1. I want you to understand that this S1, this one refers to the time step, okay, and C1 refers to class 1. So they are not related, basically. Okay, if I take this Markov chain or Markov process and extract the or construct the transition matrix. So this is my transition matrix. This is from to, right? Okay, so you can see here C1 from C1 to C2 is 0.5, from C1 to the phone is 0.5. Every row should add to 1.0. Okay, probability of 1.1. Okay, so this is the transition matrix. Okay. Now, obviously, we have defined what is a Markov process, which is basically a random process plus that satisfies the Markov property. Now we can take a look and define what is a Markov reward process. And Markov reward process is the same as Markov process plus rewards. Okay, so we go to our tuple here, and we know for Markov process we have states and transition matrix, and we add to that tuple the rewards, all right, and discount factor. So the rewards basically the rewards, it states the expected reward for the next time step, RT plus 1, given a state S at step T. Okay, notice the reward is for the next time step. Right? There is a discount factor here, and we will look at it. This discount factor is between 0 and 1. Okay, so basically here we go back to our Markov process, and we add to it these rewards. And by adding these rewards, now it becomes a Markov reward process. Okay, so the rewards are in the red numbers. Okay, so for instance, I am in state class 1. If I exit the class, then I will get a reward of -1. So now in class 2, if I exit class 2, I get a reward of -2. If I get then I go to class 3. If I exit the class, I go to a reward of -2. And in the pass state, if I exit it to the sleep state, I get a reward of +1. Okay, so basically now we are going to introduce a concept which is the return GT. Okay, is the total discounted reward from time step T. This is very important definition. The total discounted reward from time step T. So basically you can see that we are adding, so GT basically equals the reward at time step T1 plus the reward at time step T plus 2 plus the reward at time step T plus 3 plus the reward at time step T plus 4, etc., etc., etc. However, every time with the exception of the first one, I have to have a discount factor. And this discount factor for the very first reward will be gamma to the power of 0, then power 1, then power 2, then power 3, etc., etc., etc. And power of 0, we know this is a 1 multiplied by this, so we don't write it really. Okay, and you can see the discount factor, what it does, it diminishes the values of the future rewards, right, based on its value, the discount based on this the discount value. So if the discount value is close to 0 or 0, we will see that we are interested in the very near future reward. But if the discount value close to the 1, we are interested really on all the rewards that are coming in the future with the same importance as the next time step reward. So if the discount factor close to 0, then we say short-sighted, and if because we are interested in the immediate reward. And if the discount factor is close to 1, we say it's far-sighted, because you are really interested with the total amount of reward that you gain through this journey until termination. Now, the next thing that we want to discuss is the value function, and we have two things in regard to the value function. We have action value function, which is not applicable to the Markov reward process, and the state value function, which is applicable to Markov reward process and Markov decision process. So since we are in the Markov reward process, we'll discuss the state value function. So what is the state value function? The state value function gives the long-term value of state S, okay, which is the expected, the long-term value of state S, and this is equal to the expected total rewards. In other words, the value, the state value for state S really is the expected GT, which we defined just in the previous slide, given that I am in this state. Okay, so obviously you can tell the purpose of the state value is to highlight for me which state will give me more future rewards, okay, which will give me more expected return. Okay, now to compute the state value, there are two methods. We can do some random sampling and take the average, or we can use the Bellman equation. So here is our example here, okay, that we started with. And let's take an example where my starting state is class 1 and I have discount factor of 1/2. And so obviously now I'm going to assume certain sequences here that I am going to go through, okay, and from every sequence what I will do, I will compute the value for the state given that sequence. So take for example, if I'm in C1, okay, and I exit C1, so this is where C1 is right here. When I exit C1 to C2, I have a reward of -2, which is right here. Now when I exit C2 to C3, I will have a reward of -2, which is right here. Now don't forget to add the discount factor, which is 1/2 here, and we know that this discount factor, we start with exponent of 1, then exponent of 2, 3 along the way. Then when I exit state 3 to pass here, I have a reward of -2, which is right here, and we multiply it with gamma to the power of 2. And when I exit pass to sleep, I get a reward of 10, which is right here, and I multiply it by 1/8. So the value for the state given this sequence is -2.25. I would sample a bunch of those randomly, then take the average, and this average will equal to the state value. Okay, so this will be V, okay, of C1 equals the average. But I have to do good enough numbers of sequences so that my average will be accurate. Now, another way to do it is really okay. So what we did, we went on and we ran the state for. No, this is actually we calculated the state value of when the discount return is 0, and in this case the state value will equal the immediate reward, okay, which is in the next cycle. So you can see that here the immediate reward becomes the state value, and here the immediate reward becomes the state value. And the reason is that because I'm not looking for the future. I have very short-sighted mechanism of collecting the rewards. I am just interested in the reward that is coming at t+1, which is the very next time step. Okay, so this is when the discount factor equals 0. Now there are a bunch of these state values that I have that are presented here for discount value of 0, 0.10, and 1.0. But the most important thing is that how can we calculate these values other than just random sequences? Well, here comes the Bellman equation for the rescue. The Bellman equation basically says that if we want to let's go to the definition of the state value. This is basically, it says the expected return when it is given GT, and this is the expected return GT given the current state equals S. I can look at the definition of GT, and this is the definition of GT. Okay, so I'm expanding basically GT, and now I can replace this term here by the state VS, okay, multiplied by the discount factor, and this will be helpful in a second. So Bellman equation computes for us the state value of S. So let's assume that I have a state transition. A state S which transitions to S1 and S2, etc. Then the state value for S, so let me draw this. Suppose you have a state S here, and it goes to state S1 with a probability S to S1, and to state S2 with a probability of S2, etc. Then the state value of S equals the reward when I leave the state, S, plus the discounted value multiplied by the probability of going to state S1 multiplied by the state value of state S1, plus the probability of going to state S2 multiplied by the state value of S2, etc., etc. Okay, so we can use this Bellman equation to compute the state value for C3, for example, which is right here. Okay, so for C3 we can see that let me just get a color here, a good color here, which is probably a red here. Okay, so for C3 here, if I want to find the state value, it is the immediate the reward when I exit the state, which is -2, multiplied by the discount factor here, which is in this case I'm assuming it is equal 1, which is right here, right? Multiplied by the probability of going from C3 to CAFE, right? Which is 0.4. The probability of going from C3 to CAFE, right? So this 0.4 times the state value of the cave, which is 0.8, plus 0.6, which is the probability here of going from C3 to pass, which is it says here it is 0.6 here, times what the state value of pass, which is 10 here. You add up all these numbers and you get 4.3, and as you can see here is 0.43. Okay, what I just said is right here as well. Okay. Now, if you work out the math for Bellman equation, you can represent the Bellman equation in matrix form. So the vector of the state value equals the vector for the returns multiplied by the discount value. Okay, let me just okay, the discount factor multiplied by the discount factor multiplied by the transition probability transition matrix and multiplied by the state vector. With a little bit of math manipulation, we can see that we can solve for the state transition, okay, the state value by having the identity matrix minus the discount factor multiplied by the transition probability matrix, take the inverse of that, multiply it by the vector of the rewards. Now, if you do the math, you can solve the state value and plug the numbers here. One just a mathematical note: if you are trying to implement this in Python and you want to get discount value of specifically of 1 and zeros, if you plug in the 1 and zeros, you might run into some matrix multiplication and inverse issues. So don't plug in ones. Try approximate values to ones and zeros. Okay. So of course this matrix is great, solves. The problem is complexity is high. Okay. And obviously we have to use other methods that simplify the computations. We are not covering those in this lecture. Now we move to the Markov decision process. The Markov decision process, it is a Markov reward process plus actions plus decisions. So we go to the tuple of defining the Markov reward process and add the actions. Okay, so you can see that we have added those actions here, and the actions basically now we go to our state, and we introduce some modifications to add those actions. You can see here I'm adding the action of the phone here. This is an action of the phone. So if I'm in state of the phone and my action is to use the phone more, I'm gonna stay in this state of the phone. And this is C1, my class. If I study, then takes me to class 2. If I take my action is study, this takes me to class 3. If my action is study, class 3, it will take me to this sleep or pass state where I'm done. Notice I can be in C2 and I decide to sleep. This is my action, all right? Or if I'm in C1, I decide to play with the phone, for example, that take me to the phone state. And if I'm in C3 here, if I decide to walk to the cave, that's my action, then I'll be in the cafeteria here, and then there is a probability of me leaving in different places, either to C1 and C2 and C3. Okay, so this is my student Markov decision process. Again, this is from reference 1 in my that I have indicated earlier in the outline. Now, you can see that as I said, these red labels are my actions, right? They are output of my machine. Okay, so I think we talked about this, and now we talked about policy, and the policy basically defines the behavior of an agent. So given a state, what action I should take? That's what the policy answers. I am in a state here. Okay, I am in a state here. What do I do? What do I do? What action I should take? Okay, probably maybe half of the time, probability of 0.5, I can go to sleep or I can study. Right, so this is basically we're introducing the policy which really says what action I am taking given the state that I am in. Okay, so the policy defines the probability of taking certain action given certain state. Okay, this says here I can derive the transition matrix and the rewards from the Markov process, and this is should be really directly implied because the Markov decision process is originally defined as Markov reward process plus actions, and the Markov reward process includes in itself a Markov process plus rewards, and we know that the Markov process has a transition matrix that defines the probability of states of state transition. Okay, so this is really implied. What matters to me the most really is the state value. Just fix in here the state value function, okay, which calculates or which defines for me the state value, and the action value function, which both of them give me the expected return. Okay, the expected return starting from a state and taking and then following a policy. Okay, so both of those, the state value function and the action value function, they tell me the expected return of a state or an action, right, when I follow a policy. And their definitions for the state return is very similar to those we have seen in the Markov reward process. But for the action, we have to take the action into consideration when calculated or when calculating the expected return. Okay, so you can see here here the action when I present the condition for it has to be in state S, and we have to take action A. It is important to also realize that this is basically what I want. I want to have the best action value for my Markov decision process, because what comes as an output of the Markov decision process are actions, and those actions I want to maximize their returns. Okay, and the action value computes the expected return. Okay, now here is a list of equations for but what really matters to me is those two equations, right? How we compute the expected state value function, right, and the action value function, the state value function and the action value function. These are the formula, and now what we could do is that we can take my definition here of the action value function and plug it in here, and therefore I can express the state value function as a function of other state value functions. And it is important for me to this is important for me to build a linear system that can be solved. Similarly here, notice this action value function is expressed here in terms of state value function. So I can take the definition here, this definition, and plug it in here. Then now I can get a action value function, which is a function of other action value functions. And again, this is important for me to build a linear system which I can solve. Okay. Now, let's show this example, and we will show numerically what these formulas mean. Okay, so the state value function is defined as such, and let's try to measure it or express it for state 0. This is a state 0, and I have an example here. So for state 0 to compute the state value function, it is equal. Now notice this is state 0 here. It can go to state 1, S1, or this action A1 takes me to state 1 with a reward of 1, and action A2 take me to this juncture here where I have a probability of P2 going to S2 and P3 going to probability to S3, and probability of P4 going to S4. And by leaving with this action, I get a reward of R2. Where if I take action 3, I will get a reward R3, and then I'll land in S5. Now, so the state value of S0 equals action A1 multiplied by the action value function. So action A1 multiplied by action value function when leaving S0 using the action value function when leaving S0 using action A1, plus A2, which is action 2, multiplied by the action value function when I'm leaving S0 using A2, plus action 3 multiplied by the action value function when I'm leaving state 0 and going using A3. Now, the interesting part here, so you can see that basically I'm just reading those values here. Okay, so what is the action value function? This action value function of action A when I'm leaving S0. Well, this is equal. So now I'm focusing on this side here. Let's see if I can use a laser pointer here. For this one, I'm focusing on this side now. Okay, so notice I'm focusing on this side. So this is equal when I'm leaving S0 with action A1, I will get reward 1, which is right here, and I am going plus the state value of S1 here discounted by the discount factor. Similarly, if I'm leaving for action the action value function of the action A3 leaving S0, it is equal, focus right here, it is equal reward 3 plus the discount factor multiplied by the state value function of S5. Now it gets a little bit interesting if I'm looking at this here, because my next state has a probability, right? So the action value function when I'm leaving S0 using action A2 equals the return R2, which is right here, plus a discount factor multiply probability of 2 going to going to state 0, so I multiply by the state value of S2, plus probability of P3, which is right here, multiplied by the state value of S3, which is this right here, plus probability of P4 multiplied by the state value of S4. Now I can take these expansions of the action values, okay, of the action value functions, and plug them in here in the original one. Then I can say that the state value function for S0 equals this entire expression. And what is interesting here about this expression is that it only expresses the state value of S0 in terms of state value of other states, no actions at all, because I replace them with I replace the actions with these functions. Okay, so that and that enables me to solve this linear system. Now, similarly here, I can let's compute the action value function here with let's compute the action value function of let me stop here. Okay, so to compute the state the action value, the action value function when leaving state 0 using action 2, which is right here, okay, this is equals to the reward R2, okay, plus the discount multiplied by these probabilities. I have a probability of P2 going to state S0, so I multiply probability P2 times the state value of S2 plus P3 times the state value of S3, P4 times the state value of S4. Okay, now we notice now if we focus on state S2 here, we notice that S2 can be expressed as an action 7. All right, S2, I have an action 7 multiplied by the action value of action 7 when leaving state 2. Similarly here, if I look at state 3 here, it is equal to the action 8 multiplied by the action value of action 8 when leaving state S3. And similarly, I can replace the state value S4 by multiplying action 9 with the action value function of when A9 leaves state 4. We plug in these the expansions of the state value functions in the action value function, and I get the action value function for A2 leaving S0, and I get reward 2 plus this expression. Notice that all of it are action values. I replaced all the action states, and again, this is important for me to solve the linear system. Okay. Now, here are examples. Let's go back to our class example here, and let's say assume that we have a policy of 0.5 chance of going to the next state and a discount factor of a 1. Okay. Now let's calculate the state value for the phone here. The state value for this phone, this state right here. Okay. So this is equals the action A1, okay, times phone to phone. Okay, and this A1 is so when I leave from state phone by action of phone, I multiply this A1 because I assume that all the actions are 0.5 times the action value of going from leaving state phone using action phone plus 0.5, this A2, times the the action value of having action quit as I leave state phone. Right now, I can take those now and recalculate them. Right, this one here, and this one here as well. So notice here the action value for a phone equals what? It is the action value for a phone leaving a state phone. It is the reward -1, which is right here, the reward of -1, plus the discounted value, which is 1, I'm assuming it's 1, times the state value of the phone, which is -0.2. So that gives me -3.3, which is the action value when I'm applying action phone in a state phone. Now, if I'm applying the action quit on a state phone, what's the action value? Well, it is the reward, which is 0 right here. So this is 0 plus 1 times, so this is the discount factor, plus 1 times, so I come in here 1 times -1.3, which is when I go to this state, which is C1, the state value is 1.3. Okay, so you do the math, it's -1.3. So I replug the values here and I get the state value for the phone is -2.3. One thing you should notice here, this number here, it's a probability, because when I'm leaving the phone, I'm coming here, there is no branching that I say I can go to here or here or here. No, I'm for sure leaving. Oops, sorry. I am for sure leaving to this. So the probability is 1 here, and the probability is 1. So this is an example of computing the state value. So let's take a look at if I want to compute an action value here. So for example, let's see for example here. Okay. All right. So let's compute here the state value for C3. The state value for C, which is this one right here. Okay. This is equal the 0.5, which is the action, going from C3 to KF, which is right here, right? Now I need to compute the action value of KF leaving C3, and 0.5 of action study leaving C3. Okay, 0.5 times the action value of the action study leaving C3. Now let's take a look here and see what I can do with this. So with when I'm leaving state 3 and going to the cave, what happens? Well, I have the reward, which is 1. This is the reward, times the discounted factor, which is 1. And then you can see that I can go to either one of these 3 states, 1, 2, 3, by this probability, right? And every probability I multiply the state value, right? That comes to 4.8. Now the action value of C3 of a study leaving C3 is so this will be this branch now is the reward plus the discounted factor plus 1 multiplied by 0, because the state value for sleep is 0. You add all this together, right? It becomes 10. Now I can plug in all these what I found in terms of intermediate value of the action values, right? And I can say that now the state value for C3 is 7.4. Okay. Now this is given a policy of 0.5 and an action value of 1. Now, Bellman equations simplify things a lot, and this is the solution for it. For given a certain policy, so I can solve for Bellman equation. And really what matters to us is when we solve these state values and action values, we are looking for the optimal state value, which provides for me the maximum state value function over all the policies. That's what matters to me. Okay, because I can always generate state values, but are those the optimum? And the optimum action value function, right? The optimum action value function, which is this Q star here, is the maximum value function over all policies. Okay, and we say that a Markov decision process is solved if the optimum value function is found. And when we find it, now the output, the output actions of my agent are considered the actions that will provide for me the maximum future rewards, the maximum returns. But you have to solve the Markov decision process for that to happen, which is to determine these optimal state value function and the optimum state action value function. Now, here is a diagram that shows that the optimum state value for our example when the return equals 1. And one thing to do is, for this example, really to determine these maximum state values, you can work your way backward from the sleep state all the way backward, and you can see that if you plug in the reward that you are getting, right? So here we have R equals 10. It must be the value of the state value, because after that we go to 0. So, and from 10 to go back to C2, you have to consider the R minus 2, and this makes C2 equals 8, because 8 equals minus 2 plus 10. And if you go back from C2 to C1, you have to consider this reward, and this makes the state equals 6. And if you go back to phone state, all right, you have to consider the reward of 0, and this makes the phone state 6 as well. So these are the optimum state values for the machine that we have for the Markov decision process example. Now, if we want to consider the maximum the optimal action values, and we can calculate them, we can use the optimum state values to calculate the action values. And here I give example. And suppose here in the case of the phone, we have two actions, this action and this action. Okay, so for this action, which is basically I am in state phone and I'm applying action phone, so what I do, I add the action plus the multiplication of the reward, the discount factor with times the state value. So minus 1 plus 1 times 6, and that puts me a 5, and so this is the value of the 5. This is the optimal action value for the action of leaving the phone state using action phone. So if I consider this here, for example, as well, I am going to through this quit, right? Quit action from the phone state. So this will be the reward, which is 0, plus the discount factor multiplied by the destination state value, which is 6, and this makes it the value equals 6. So you can calculate these values. You can run through them, all of them, and determine these optimal action values. And obviously we have determined them based on the determination, or we can calculate them based on the calculation of the optimum state values. Now, once we decide on the optimal action values, the Markov and the optimum value functions, the state values and the action values, my Markov decision process is solved, and now we can play the game, because I know that these actions now that are produced by this agent, okay, these actions now will give me the maximum rewards, the maximum future rewards. So to solve this optimality, there is really no closed form. There are other forms that value iterative, policy iteration, Q-learning, and SARSA methods that are being used to solve these optimality equation. And this is an appendix of all the acronyms in this lecture. I know there are a lot, so I put them in one slide here just as a reference for all of you. And this brings me to the last slide of this presentation, and thank you very much.